Both lights might be a little too much. You know what I'm saying? No? No? Do both lights? Both lights? That's what we're feeling? So, I'm going to walk you through what to fill in for each spot, and we will be good to go. So, fission and fusion. So, I'm going to give you a little background information before we actually get into the details of fission and fusion. Okay, so the goal of today and tomorrow is the essential question. The essential question: how is energy unleashed from atoms? How do we create energy? All right. Where does that energy come from? How can we create it? And how can we use it? All right. That's the goal. All right. How is energy unleashed? Unleashed the beast from atoms. Okay. The best part about this is like you can color in practically anything and everything. I love that. Everybody got the question down? Sweet. Okay. Now, where it says topic question number 1, where you see topic question 1, that is right here. What particles make up the nucleus of an atom? All right. Like I said, we're going over some background information, and hopefully we kind of remember what particles make up the nucleus of an atom. Right? Now, hopefully we remember the nucleus has the neutrons and protons, which means where are the electrons? Where are the electrons at? Say what? What'd you say? A magnet? Around it. Around it in what? What's it called? You're right. You're exactly right. It's called, the electrons are in the electron cloud. All right. So where it says the nucleus of an atom is composed of 2 subatomic particles. So you're going to fill in subatomic particles. Okay. Let's see, what else do we need to fill in? Protons. The charge of protons is positive. The charge of neutrons is neutral. Now the overall charge. What would the overall charge be in a nucleus? If I have positive ions, I have neutral ions, what's the overall? Is it going to be negative, neutral, or positive? Overall. Positive. Very good. Overall, it's going to be positive. So there was a little box there. Overall charge of a nucleus is positive. Okay. This represents the nucleus of beryllium because there are 4 protons equal to the atomic number. Isn't that fantastic? What? Isn't that fantastic? Yeah. It's a great sharpener right there. Equal to, there are 5 neutrons in this isotope. Can you guys read that in the back? Yeah. Somebody, if you guys want to move forward, you can. So what? That light, I don't know how, no. Would you like to scoot up? Got a seat right here. Got a seat right there, right there, right there, right there. Okay. So positive, neutral, positive, fill in the blanks. How you guys doing? Any questions so far? So the nucleus has protons and neutrons. That's key because all fusion and fission is, we're talking about the nucleus of an atom. Okay? But now we introduced a new term, isotope. Okay? Isotope. So let's learn about isotopes real quick. Next topic question. Topic question 2 is, what is an isotope of an atom? What is an isotope of an atom? Okay. What is an isotope of an atom? So that's a question. Okay. What is an isotope? So an isotope is atoms of the same element that have different numbers of neutrons. Atoms of the same element that have different number of neutrons. Now, at the bottom it says, color the protons with your choice of color, then color the neutrons with your choice of color, and then count each and write them on the lines. So we're going to do some coloring in. All right? Going to color those in. Color all the protons in, color all the neutrons in, count them. All right? Let's try this out. Whoa. Hopefully those are right. Okay. that what you guys are getting?
Oh, yeah.
Yeah? Awesome. Okay, so over here, it says, what do they all have in common? Well, if you look, you might still be drawing, that's fine. What do they all have in common?
16 protons.
16 protons. That's exactly right. They all have 16 protons. Now, 16 protons tells me what element it is. What element is 16? Sulfur. Very good. Sulfur. So when you look at the isotope notation, our element is sulfur. Okay, our element is sulfur, and there's a -32. The reason we have a -32 is because we add up the mass of our protons and neutrons. So once again, if I have 16 protons, I have sulfur again, right? Number 16 on the periodic table is sulfur. However, what's the mass of this sulfur? What's the mass of this sulfur? 16 plus 18? 34. What's the mass of this sulfur? Maybe 41? So that is an isotope. Isotopes are the same element. They're all the same element. Sulfur, sulfur, sulfur. However, different number of neutrons. That's what it is. How do we feel on that? Do we kind of remember neutrons pretty well? All right. Is everybody good to move on? All right, let's rock and roll. Might need to erase some of this.
Maybe.
Got a lot of dots. Okay. So my new question, question number 3. Let's see if we can answer this. What is nuclear fusion and how does it happen? What is nuclear fusion and how does it happen? That's our new question we got to solve. What is nuclear fusion and how does it happen? Okay. What is nuclear fusion and how does it happen? So if we look on the side, I'm going to do the side one. Fuse, F-U-S-E, fuse stems from Latin and means to melt. All right, melt. Okay. With high temperature and pressure, lighter nuclei combine to form a larger nucleus. Okay. This needs temperatures for over 10 million degrees Celsius. 10 million degrees Celsius. That is insanely hot. And that's why it only takes place, as of now, and the sun and other stars. Okay. Now, on Earth, have we solved what fusion is? Do we know? Like, can we create fusion ourselves? No. Are we close?
No.
Oh, on the contrary, we're really close. I'm not really close, but like the world is really close.
I'm really
We are really, really, really close. And there's actually two ways we're doing this. So we have to fuse, right? We have to create something so hot that two nucleuses are going to come together and bond. One way, we're using magnets. Okay, we got super strong magnets. And I'm going to show you a video that shows that. A second way is we're using lasers. We're using the most powerful laser in the world trying to solve fusion. Pretty cool. Say that a little bit louder. Like what do you mean by how strong? I don't know. I don't know what the hardest thing it could cut through. I don't know.
Because like there's laser players.
Yeah. All right. Everybody have these words written down? Sweet. Now, this is how fusion works. Okay? So, the isotope of hydrogen with a neutron, with one neutron, is called deuterium. That is deuterium. Okay? Or heavy hydrogen. Okay? The hydrogen with one neutron is called H2. Okay? A helium-4 nucleus, which has 2 protons plus 2 neutrons. Okay? And it does not produce radioactive waste. Okay? Does not produce radioactive waste. So if you look at this, the sun has a lot of heat. What it does is it takes the deuterium, boom, boom, melts it together, right? And if we have H2 and H2, we create, so let's think about this. Hydrogen, how many protons will I have if I combine these two? How many protons? 2. What element is number 2? Helium. If I add up my entire mass, what is 2 plus 2? And that's how you get helium-4. All right? When we create helium-4, is that an alpha, beta, or gamma? Alpha, right? So we create an alpha particle from fusion, and it creates so much heat that it can fuel so much. And that's why we're trying to get this. That's why we're trying to create it. But the biggest thing is, it does not produce radioactive waste. That's the goal. And what we do know how to do, we know how to do fission. Right? We know fission. We solved it. All right? We're about to go over fission next. But fission creates radioactive waste. All right? Where do you think we store that radioactive waste?
Nuclear power.
We create waste from nuclear power plants. Where do we store it, though? Some goes in the atmosphere, yes. Very good. In Earth. We dig a big hole. We dig a big hole and we put it right in Earth. No, I mean, kind of. Not really. So we put it in barrels. Radioactive waste goes in barrels. Okay? We dug a big hole, put the barrels in the ground, and where it's out right now.
Hope to God that something.
Exactly. So that's why we're trying to create fusion, because fusion, we don't have that waste. Okay? But fission, we do. Fission, we do. Have you guys heard of Chernobyl?
Chernobyl?
Yeah.
The big power plant.
Yeah. Yeah. That's a big power plant that had radioactive radioactive material that like it exploded, right?
It was a long time ago.
It was
It's
about
still
30
highly-
years.
Yeah, it's still highly irradiated.
It's actually fascinating. If you look up pictures, well, maybe at the end of class, we'll look up some pictures. It's pretty cool. Like so it's an abandoned city, right? No one can go there. It's super radioactive, but like animals can survive there. Okay, so like the animals are just like walking around in buildings, you know. So what? I missed that the second
You know,
part.
like what if like they get like radiation off in them and they're like some weird.
Oh, no, they're still good. They're still normal. Like their genes might have been affected to cancel out the radiation, but yeah, they're still good. All right, so that is fusion. Fusion is fusing the two together. All right, we're gonna start fission. We're not gonna get all the way through. We're gonna do one more slide. One more. Okay. Last one. Last one. Question number 4. What is fission? All right, we know what fusion is. We solved that question. What is fission now? Now, if you think about it, fusion was fusing two things together. What do we think fission is going to be? Taking things apart. Taking things apart. That's exactly right. We're going to take some things apart. All right? All right. So if we look at this, oh, wrong one. If we look at this, got the question. Fis, F-I-S-S. Fis stems from the Latin, means to split. All right, we're splitting things up. That's fission. All right, so we're taking a nucleus and we're splitting it up. All right. Now, fission is releasing the energy of an atom by breaking a large, unstable nucleus into smaller nuclei and particles. Okay? And way at the bottom, it says takes place in nuclear power plants, or I guess just nuclear power plants, and in atomic bomb. Okay? It's kind of scary. They're built the same. Like we use what we used it for atomic bomb to create energy for our houses. Wild. That is crazy. Like if one thing goes wrong, yeah.
Have you seen like those apocalypse movies where it's like a couple of years or something later? Well, most people would be dead because like you know,
True. So it's just fascinating, and we're going to actually look more in depth on a nuclear power plant. Super fascinating stuff. Now, fission created the atomic bomb, right? We used the atomic bomb in Japan twice, right? Hiroshima and Nagasaki. Have you guys heard of the hydrogen bomb? So America has created the hydrogen bomb. Okay. Instead of fission, what do you think the hydrogen bomb uses? Fusion. They use fusion. Now it's wild because the hydrogen bomb is about I think the number I read was 230 times the atomic bomb. Think about that. 230 times the atomic bomb. Why do we need that? We don't. Like, why do we need that? There's no, I don't know. But that is, so fission is breaking things apart. Okay? Yeah. that's where I want to stop. We got about 8 minutes left. All right. But what I will show you here, I'll show you some pictures of Chernobyl. It's actually pretty interesting. All right. Light, front lights coming on. 3, 2, 1. Back lights coming on. 3, 2, 1. All right. So you guys can put these notes away.